Okay, so yes, so let's continue our discussion on the ideal solution, and I think this is what we stopped last time. So just to give us a very quick recap of what we have discussed about the ideal solution. So we set up a very simple system, right? So say that we're just going to look at two different states and trying to figure out if we have this phase separate state as a reference, how can we find the free energy for this mixing state, right? And we go through all the details about definition of solid solution, a more fancier version of distinguishing configurational entropy versus vibrational entropy, and then we proceeded to figure out what is the configurational entropy for the solution state, and find this very helpful, useful expression, and then work out the mathematical details and have this very nice expression for the entropy of mixing for the ideal solution. And we go back to find out the free energy for this mixing state. Right? So that's what we have, I think, have done in the last lecture. And then this is the final expression that we get from the all the analysis. As you can see that in this system, we call this an ideal solution because it does not have any contribution. The free energy has no contribution from the entropy terms, right? So basically this means, you can consider a scenario that the A and the B atoms, they do not distinguish neighbors. It doesn't really matter whether the bonding neighbors are A or B type, they have the same contribution of the interaction energy. So in this case, from the interaction energy point of view, the system does not distinguish different neighbors. So there will be no contribution from the enthalpy due to the mixing. And the only contribution will be this part, which what we call the contribution from the entropy of mixing, and we derive all of this together. So when we plug this back into the free energy expression, this part corresponds to the free energy of the reference system, right? So if you just have a simple collection of a portion of A and a portion of B, the free energy for that system is going to simply be a linear combination of the molar free energy of pure A and pure B weighted by the respective the molar fraction for both A and B. So we just have that part here, and this is the change due to the mixing, and we add this part here. So altogether, we get a free energy for the solid solution state, which is this one. Okay, so that's, I think, what we discussed in the last lecture. And one thing that I think we briefly mentioned at the end of the last lecture is that, by, kind of inspired by this very simple form, right? If you have a system and you can write down the system as a molar fraction times the so-called molar free energy, right? This is a very simple linear term that give you a very intuitive understanding of how you can express the free energy. Well, for the solid solution case, we end up with this relatively lengthy expression. Now we're asking the question, can we write the free energy for the mixing state, for the solid solution state, in a similar form as for this simple combination of the molar free energy times the molar fraction? The answer is yes, right? So if you look at this expression, you just take out all the terms, have this XA in here, and then regroup this term and take out XB, you can have this expression, right? And then we have two new quantity called mu A and mu B, but if you write down them, okay, by simply, so this equation can be very easily derived from this one. So mu A is simply this one, the molar free energy for the pure A plus this term, and mu B is the molar free energy of pure B plus this term, okay? So we call these mu A and mu B the chemical potential, okay, in our class, okay? So, and it's also based on this particular form, it's fairly easy to see what is the physical meaning for the chemical potential, right? Because if you compare again for this case, for the demixing case, we know clearly GA and GB playing a similar role as the chemical potential, right? It's the molar free energy of pure A and pure B, right? If I give you a pure A, like in this part, the molar free energy is GA. And similarly, for I give you a pure trunk of B, the molar free energy is GB. So if you think about this way, okay, chemical potential can be considered as the molar free energy of either A or B atoms, but not in the pure state, but in the mixing state, right? So it's still a molar free energy. And so you can get the overall free energy by simply modifying the molar free energy by this relative molar fraction. and similar for this part, right? So it's a molar free energy of A and B, but not in this pure state, in the mixing state, okay? And we analyze this form of free energy, and we basically can clearly see that this Ga corresponds to molar free energy of the pure phase, of the pure state, but then you have something extra term, right? And this term, based on our analysis, is definitely come from the fact of mixing, right? Otherwise, you're going to have only this term in the pure state. But if you mix them together, you get a molar free energy in the mixing state, and the extra term have to because of the effect of mixing, okay? And I think I asked you this question before. What is the sign of this term, this RT log XA? Is this positive or negative for non-zero XA?
Positive.
Negative, right?
This is negative, right? Because XA is always,
Yeah.
XA is a molar fraction, always going to be
Smaller than
greater than 0 but smaller than 1, right? So you take a logarithm of a number smaller than 1, you always get a negative number. So what does this mean? If this is negative, then this mu A should be greater or smaller than GA?
Smaller.
Smaller than GA, right? So, and does this make sense to you?
Yeah.
Yes, right? Because we already said from our previous analysis that if you're mixing these two, I think you have to mute. I'm sorry, I heard some echo. So if you mix these two systems, we know that for any finite temperature, for any composition not equals to 1 and 0, right? If you mix them together, the system basically brings down the free energy. So I guess I want to show this before, right? So this is delta G mixed, depending on what temperature you have, but as long as it's finite temperature, for any non-zero and non-unity molar fraction, you're always going to bring down the free energy, right? And this reduced free energy has also to be reflected in the molar free energy of the two systems, right? Because you keep the molar fraction the same if the overall free energy is reduced. So the molar free energy of each species has also to be reduced. So that's quite, consistent with our analysis. So this means that, okay, when you mix A and B atoms together, the molar free energy changed by this particular term compared to their pure state. And in this particular example of ideal solution, because mixing reduce the overall free energy of the system, so therefore mixing also reduced the molar free energy of both A and B atoms in the mixing state. So this means that mixing reduced the chemical potential in this particular system. Okay, so that's kind of a very interesting way of understanding chemical potential. Now, again, I understand if you already took some thermodynamic classes, you probably have a different terms here. Typically, you have a symbol called A, activity. We'll show that later because this XA is the activity in the case of ideal solution because there's no enthalpy, there's no interaction. So the only thing that contribute to the enthalpy to the free energy and also to the chemical potential going to be the effect of entropy that only depend on the molar fraction. But we will show that in the case of regular solution, we will take into account the interaction effects. This term going to become the so-called activity, which is going to be consistent with what you have seen before. Okay, so that's a very kind of interesting way of looking at the chemical potential. So I hope after this discussion, whenever we see chemical potential, the first thing come into our mind is that chemical potential is a molar free energy of one of the atoms in the mixing state. I think that's probably the best way of using this in the rest of the class. Okay, so not only that, this chemical potential has a very, kind of intuitive, understanding. We also have a very nice way of graphically look at this term. Okay, so now if we go back to this equation, now suppose that we can write down the free energy in terms of mu A XA plus mu B XB, right? So suppose we can write this. And we know that this is not a straight line, right? If mu A and mu B are constant, this is going to be a straight line. But both mu A and mu B are going to depend on the molar fraction of the atoms. So eventually the free energy is going to become this, right? Become a curve like that. Okay. However, okay, if I'm only looking at a particular composition, say if I fix mu A, or I'm sorry, if I fix XA or fix XB, okay, now in this particular case, mu A and mu B are going to be constant, right? That makes sense to you? So now this allows us to find a very, kind of very helpful and very useful, actually, graphic interpretation of the chemical potential. Okay, so how would you do that? Now, suppose I choose a particular composition. Now, in this case, I use XB. to describe my composition, and XA is trivially related to XB as 1 minus XB. So now if I fix XB, I also fix XA, right? So now suppose I choose a particular XB right here. Now I think in this case, XB is the lowest point in the free energy curve, but you can definitely choose some point here or anywhere, okay? They're the same, but I happen to choose this particular point, okay? But there's no significance about its minimal nature. So I choose this point, okay? And then what I do is that now if I take the derivative of the free energy curve right at this point, okay, I can get a slope, right? And then what I do is that based on that slope and based on this particular point, I construct a straight line, okay? Does this make sense? So basically this particular line is simply the tangent line to this particular point I'm choosing here. It past this point, a tangent to the free energy curve, okay? That makes sense to everyone? So this is how I construct this particular line. And this line have an intersection with this axis, which xb equals 0. This is a pure A axis. And it has an intersection with this pure B axis, where xb equals to 1. Okay. And an interesting fact is that this interaction corresponds to the numerical value of mu A corresponding to this particular composition you choose here. And this point corresponds to the numerical value of mu B associated again with this particular composition you choose. Okay, does this make sense to everyone? One thing you can see this very easily is that, again, this is just a clear, kind of a simple way to see why this is the case and not the rigorous way. But you can basically see, okay, assume that mu and mu B are not changing, a constant, right? So if I just take a derivative of this free energy functional with respect to xb, for example, and I literally get this straight line with these two intersections being mu A and mu B. That's the easy way to see this. A more difficult way to show this is that, I think I'll leave this as a homework, is to go back to the free energy curve and do the derivative and do some mathematics. And we will see that, again, the intersection is going to be exactly mu A and mu B based on the expression. Okay, so now
sir, I have a question.
Yes.
What if we take a point somewhere else, like on the curve, like not in such a way that if we draw the tangent to the point,
yes,
so it just touches just one axis, either A or either B. So then what would be the value of chemical potential in that case?
No, so for any point except for these two, you can take any points on the curve except for the pure A and pure B.
Yes, suppose if we take between the point you have taken in between B, so between A and the middle point at the bottommost point, if we take anywhere between that, so what will be the, if we draw the tangent, so the tangent will not touch the A axis, right?
No, it will. It definitely will, because it's just going to go like this.
Negative.
See, it's just a little bit further down, but it eventually going to still touch the axis, except for if you reach here, because I didn't show, this axis is going to go forever. It's just not this finite scale I'm showing here, right? So it doesn't really matter as long as you're not reaching this point. If you're reaching this point, then we're getting, kind of in a pure matter. This is a pure substance, and you get one of the chemical potential goes to minus infinity, and that's definitely not the case. But for any state, for any mixing state, doesn't really matter. You choose that particular point. If you do the tangent, you can always get two numbers. Okay, the reason why you see here, so at the minimum point, you see that mu A and mu B are roughly on the same level of their numerical value. But if you choose at this point, because you have definitely much more B than A, the chemical potential of mu A is going to be significantly reduced, because the entropy change by adding a small amount of A into B is going to give you a huge increase. So that's why you see a much lower mu A in those cases. And for the same reason, you will see much lower mu B if you choose the point, for example, along this line. For example, something here, right? You see that mu A going to be higher than mu B. And this is because that if you just add a little amount of mu B, right, this is going to significantly reduce the chemical potential of the mu B, because it wants more happier in those cases, right? So good question. No problem. So let me go back. Yeah, sure.
So does this essentially mean that that we're saying that the molar free energies changes is if we change the composition?
Yes, of course, right? Because as you can see, the molar free energy change as a logarithm of the chemical potential, or the molar free energy of the species in the mixing state change as a logarithm of the molar fraction. So it's changed in a nonlinear fashion. The chemical potential is a function of the molar fraction,
Okay.
depending on how much, depending on how much you add the atoms or how much you mix them together.
Yeah. Thank
So
you.
it's always changing. Yes. Good question. So yes, so I think that's pretty much all I want to say about the chemical potential. Okay, so for the ideal solution, yes. Okay, as another thing I want to point out is that, you know, if we look at this expression, okay, and because we know that the free energy curve, you know, this guy gonna give you GA when for the pure A case, and it's gonna give you GB for the pure B case, right? But now if I choose a particular composition, I get mu A and mu B, right? These are the molar fraction in the mixing state. So the difference between the mixing state and the pure state, we know going to be this guy, right? The contribution due to mixing in the case of ideal solution. So this difference, okay, the numerical value for this difference is going to be given by this and this correspondingly. Okay, so that's another way of using the graphs to see the meaning of chemical potential. And you can clearly see that by mixing these two atoms, for the case of ideal solution, the molar free energy for both of them does, has been reduced compared to the molar free energy in the pure case. Okay, so I think that's pretty much all I want to share with you for the ideal solution. But again, this last idea of using a graphic representation for the chemical potential is going to be very, very helpful for our understanding of more complex systems, especially when we apply this to phase equilibrium. Okay, as we'll show later, probably not this lecture, but probably on Thursday. Okay, so yes, that's all I want to share with you about the regular solution. Again, this is, I think, the topics that we have described. Yeah, I think I quickly went through this in the beginning of the lecture. So I'm going to now switch gear and talk about a more interesting situation. Let me see. Okay, so let me start share. Okay, can you see my new slide?
Yes, we can see lecture 3.
Okay, lecture 3. Yes, good. So yes, so in lecture 2, we talk about ideal solution, right? The point there is to introduce the concept of solution and focus on the effect of entropy. But I guess I got a lot of questions that, you know, how well the ideal solution model can really describe a alloy system. And my answer is, you know, in most cases, wouldn't do a good job because it ignores completely the contribution from the interaction of the atoms, which is enthalpy. And this is not true for many real solutions, many real alloys. So here, we're going to introduce a more realistic model, okay, for these binary alloy. Okay, this is so-called regular solution, okay. Again, so here are the topics that we're going to go through, hopefully, this week. Okay, so first I'm going to introduce the definition of regular solution. As you may already can get a sense of this, because in the case of ideal solution, we only focus on the entropy of mixing. So here we have to add back the effect of enthalpy of mixing, and that exactly one of the major things that we would do here. Okay, and then after we talk about the enthalpy effect, and we're going to see that the temperature here plays a very non-trivial role. Because if you look at the case of the ideal solution, we show that for any finite temperature, the system is going to always favors the mixing state, right? Because that's going to increase the entropy, which reduce the free energy. But here, when the interaction play a role, you know, the temperature is going to play a non-trivial effect, and we're going to see a prototype phase transformation going to emerge from our analysis of free energy curve. That's going to be quite cool. And then we're going to introduce activity, which is, again, a fancier version for the chemical potential to deal with chemical potential. And then we're going to talk about, you know, what are the insights that we learn here can be really applied to real solutions. Because, again, even the regular solution is a better model for real solutions, but they're not real solutions. There's still some effects that we ignore. So we're going to point out, you know, exactly point out what are those effects that we're ignoring, right? But we're also going to point out what are the insights, at least the qualitative insights that we learned from this model can be applied to real solutions. And then we're going to talk about some, Alder phases and intermetallic compounds, which are typically seen in real solutions, which we do not consider in our model. So that's going to be the plan for this. Okay, so again, quickly recap our setup, right? So when we talk about the regular solution or ideal solution, the key thing is that we want to know if in one case we have a phase separate state versus a solid solution state, which one going to be more stable. And we have been doing this for all the time that to see which one going to be stable, we will compare their Gibbs free energy, and in this case, molar Gibbs free energy, right, for the system, and based on our setup for the ideal solution, which is also true for the regular solution, the easiest way to do this is to focus on the so-called difference of the free energy due to mixing, right? In this case, we have a demixing state. In this case, we have a mixing state. So we get a contrast between these two states. And this gives you the so-called free energy of mixing. And then we consider this free energy of mixing has two contributions, one from the enthalpy of mixing, the other one from the entropy of mixing. And for the last two lectures, we spent our time focusing on working out the entropy of mixing, right, for the case of ideal solution. Now we're going to return to the enthalpy of mixing. So in the case of ideal solution, we basically define ideal solution as one in which the enthalpy of mixing always equals to 0, right? And clearly you can see that for the regular solution, okay, we're going to deal with cases where this enthalpy of mixing is not 0. Okay, it can be either positive or negative, but it's not going to be 0. Okay, so now here I can have a question for you. So if this enthalpy of mixing is positive, okay, if this enthalpy of mixing is positive from this energetic point of view, from the interaction energy point of view, does the system favors the mixing or mixing state?
No, it won't favor the mixing.
Demixing.
It's going to favor the demixing
It
state,
is
right?
mixing.
So if this enthalpy of mixing is greater than 0, okay, from the interaction energy point of view, does the system favors the mixing state or the demixing state?
Demixing.
The demixing state, right? Because mixing increased the interaction energy, right? So this means that when the atoms have neighbors of the same type, they're happier in terms of their interaction energy, have a lower energy. If the atom have neighbors of different types, they're not happy because this increased the energy, interaction energy, right? Now, for the same reason, if my .H mix, enthalpy of mixing is smaller than 0, this means that the system favors mixing. The system favors mixing from the energetic point of view, right? It favors to have neighbors of different types because this is going to reduce the interaction energy. Does that make sense to everyone?
Yeah.
Okay. In that system, do we going to ever see a phase transformation at any finite temperature? In the system where the enthalpy of mixing is smaller than 0, do we ever going to see a phase transformation?
No.
No, right? Why is that? Because we know the entropy of mixing always favors the mixing state, because you can, by mixing, always increase this guy. And we have a negative sign here, so this means that this contribution can always be negative. So it favors mixing, right? Now, the only term that can possibly compete with this guy going to be the enthalpy of mixing. But now, if your enthalpy of mixing also favors the mixing state, which means that by mixing, you decrease the interaction energy, these two guys, so these two contributions will all favors mixing. So there's no way for you to go back to the demixing state. This is independent of temperature, right? So for those systems, the behavior will be fairly boring. You can always see mixing is the favored state. Did that make sense to everyone?
Yeah.
Okay, so now in the other case, if your enthalpy of mixing, this guy is greater than 0, you see that we can have a chance to set up a competition between the enthalpy of mixing and entropy of mixing. And the key factor that determines which term or which effect will win this competition is the temperature. Okay, so we're going to discuss that in more detail, but for now, I just want to give you some appetizer that we're going to see a lot of interesting behavior because of the fact that the enthalpy of mixing is not 0 in our system of regular solution. Okay, so anyway, that's the the definition of regular solution and the significance of that. So yes, again, if we want to, basically the key concept is, the key idea is to find out the free energy of mixing, but now we have to work out the two terms. The first one is the enthalpy of mixing, the entropy of mixing, and now we have to worry about the enthalpy of mixing. So here is the first assumption that we make, okay, which is different from the real solution. We assume that all our analysis that we derived for the entropy of mixing for the ideal solution also applies here. Okay, so this means what? This means that all of the possible configurations that you have for the ideal solution, you also have them here with equal probability. And we know that is not the case, because if you impose a non-zero interaction energy, not all of those configurations are going to be equally favorable, right? But for now, we do not distinguish that. We still consider that all of the configurations that contribute to the entropy of ideal solution also play the same role here. So that is our first assumption, which make this is just a model for the real solution. Okay. But anyway, so the good thing is that, okay, with that assumption, we don't have to rework out the expression for the entropy of mixing. We can just take whatever we derived from the ideal solution case and use the expressions here. Okay, so that's a good thing. So the key thing that we're going to work with is what is going to be the effect of the enthalpy of mixing. So basically, we're going to work out an expression for this guy. Okay, so now, because we know the enthalpy of mixing comes from the interaction energy, right, between different type of atoms. So we now need to go back to find out a model for the interaction energy. Now, if we want to solve this recursively, even in the solid state, we have to go back to the ab initio calculations probably for the DFT or density functional theory to find out the electron states, the bonding energy, etc. But in our case, because we're only consider this as a model and we want to work out something analytically, so again, we use the second assumption, right? We assume that the interaction energies only come from the nearest neighbor interactions. And this means that, okay, if I have a B atom right here, I only consider that the contribution to the interaction energy come from these BB bonds, AB bonds, AB bonds, and BB bonds. Okay, we'll only consider the contribution with nearest neighbor bonds in the system. And for a binary solution, the good thing is that you only have 3 types of bonds, right? You only have AA bond, which is rare, and BB bond, and AB bond. And we associate, and again, we do not consider, the vibration is going to change the energy and things like that. We assume that if you have a particular type of bond, and this bond is associated with a fixed energy, again, this is convenient for our analysis, but this is assumption. Okay, so for each of those bonds, we're associated particular type of energy. And for the AA bond, we have epsilon AA. For the BB bond, we have epsilon BB. And then for the AB bond, we have epsilon AB. Okay, so this is our setup. Now, with this setup, okay, I'm sorry, this one should be coming out later. But anyway, so with this setup, we can easily write down the enthalpy for this demixing state, right? Because in this case, the only thing you need to do is to count the number of AA bonds and number of BB bonds, right? And as we said before, we ignore this interface, or you can consider we just, literally put them together, but do not impose the proper condition for these two guys to form bonding. So we only need to worry about AA bond and BB bond. Okay, so this is, again, the energy associated with each AA bond. And I'm sorry, I think this should be N, lowercase n AA. Okay, so this is the number of AA bond in the demixing state. And this NBB is the number of BB bond in this demixing state. Okay, so this is quite straightforward, right? We just write down the interaction energy in terms of the energy of each bond and the number of the bond in the system. Okay, but we're not quite okay with this expression because we want to express this enthalpy for this demixing state not in terms of the number of bonds in the system, although we start with number of bonds because it's easier for us to count, right? It's easy for us to write down the expression, but the number of bonds is going to change if you change the states, right? If you mix these two, and the number of AA, BB bonds is going to all change. So that's not something intrinsic to the system. So we want to do some, further thinking to write down the enthalpy of this demixing state in terms of more intrinsic properties of the system, okay, such as the number of A atoms and the number of B atoms, which are not changed before and after mixing. Okay, so now the key or the trick to convert this AA and NAA or NBB to the number of A and B atoms is based on this observation. Okay, so now let's just pick one A atom, any way A atom in the system, and we have a very simple square lattice. We're gonna based on the square lattice to do our counting, but this counting can be generalized to other coordination number. Okay, and in 3 dimensions as well. So but let's just work with the square lattice. So each A atom has 4 bonds, right? Can we see that clearly? If you do not see that, I think this is even clear. So each A atom have 4 bonds, right? And this is a mixing state. So if we go back to this, which we have this demixing state. So each A atom have 4 bonds and all of the neighbors are A atom, right? So this means that each bond is equally shared by 2 A atoms. Now, based on this relation, how many bonds is effectively associated with a single A atom?
1/2.
So if we do this naive counting, it seems like that each A atom have 4 bonds, right?
Oh, sorry, yeah, each eta, yeah, 4.
But each bond is equally shared by 2 A atoms. So by considering these 2 effects together, how many bonds? Okay,
We 2
2 Na, 2 into Avogadro's number of atoms.
effectively each A atom is associated with 2 bonds, right?
Yeah.
So it's very simple because each bond you can consider that you can split the bond by half, right? So it appears that each A atom have 4 bonds, but each bond is shared by 2 atoms. So each bond only contributes a half to a single atom. So basically you have 4 times a half equals 2, right? So each A atom have 2 bonds. So what does this mean? And for the same counting applies to the B atoms, right? Because they have the same coordination, basically the same coordination arrangement. So this means that the number of each A atoms is associated with 2 bonds, 2 AA bonds. This means the number of AA bonds equals to twice of the number of A atoms. Does this make sense to everyone in the system? And the number of BB bonds equals to twice of the number of B atoms, okay? And now this one's supposed to pop out now, but I forgot to add animation for this. But anyway, so you see that then we can express the interaction energy for this demixing state in terms of the energy of each bond for the AA type and the BB type, and multiplied by the number of bonds, which in this case are expressed in the number of A atoms and number of B atoms. Does this make sense to everyone?
So I have a question here.
Yeah, sure.
So the enthalpy here is the molar enthalpy of mixing, right? So shouldn't we take into account the mole fraction or the number of moles of the A and B atoms?
Yeah, you can easily express this Na as XA times Avogadro number. But here, it's easier for us to first work with numbers because it's more intuitive. But we're going to reduce everything to molar fraction.
Okay.
Yeah, good. Thank you. So yes, this is clear, right? So this is the enthalpy for the demixing state. Okay, you'll see that this is more, non-trivial than the entropy for the demixing state. For the entropy of the demixing state, we have simply 0. But here, we have to work out the counting of the atoms. But again, it's not difficult. Okay, this is the enthalpy for the first state, for the demixing state. Now, if we want to get the enthalpy of mixing, so we have to work out the enthalpy of the second state, which is the solid solution state as well, right? And the way how we work out for this particular demixing state also applies to the case for this the mixing state. Again, I forgot to add animation here, but suppose you're, pretend you're not seeing this, okay? And we'll see this as a surprise later. Anyway, so the enthalpy after mixing, this is for the solution, right? Can be worked out in a very similar fashion. The thing is that we just need to count. First, in this case of the mixing state, we only have 3 types of bonds. We have both AA, BB again, but we have this AB bond, which we do not have for the demixing case, right? But we do the same counting, right? But here we write down the number of AA, BB, and AB bonds as respectively PAA, PBB, and PAB. The reason why we use P here is to denote this is more like a probability, or denote there's a stochastic nature with the demixing. So we use the P here, and also to distinguish from the other symbols for the demixing state. Okay, so that's again the number. These are the number of the bounds. Okay, following the same logic, what we're trying to do here is that these P, AA, BB, or AB are not intrinsic to the system. For each different configuration, this number going to change, right? So we want to convert all these number of bounds to the number of A and B atoms in the system, right? So we need to do the same analysis we did again. So we already did this. Each AA bound contributes to a half of A atom. Does this make sense? This is the same thing saying that each A atom is associated with 2 bonds, right? We just use the reverse way. So each AA bound contributes to a half of A atom. Does this make sense to everyone, right? So each BB bound contributes to a half of B atom, right? Now the question is that what does each AB bound contribute? How many A atoms does the AB bound contribute, and how many B atoms does the AB bound contribute?
Two. Like in this diagram, there were 2 AB bonds for each A and B. It's probabilistic, means we don't know like how many bonds are there.
We don't know how many bonds are there, but we know if I give you a particular AB bound, what is the contribution of this? So if I know that I have a AB bound in the system,
2 atoms per 1 AB bond.
It will be half of the half, right?
Exactly. So an AB bond can only be associated with a half atom, but this half atom is further split into half A and half B. So each AB bond contributes 1/4 of A atom and 1/4 of B atom. Does this make sense to everyone? Now, if not, draw a cake-like diagram. Okay, so you can pick up any AB like here, and then because you have 4 bonds, right? Think about this. Each atom has 4 bonds, so you equally divided this atom into 4th, right? And you see that each bond is only attached to a 1/4 of this atom. Okay, I think this is the most intuitive way of seeing this. Can you imagine that? Because I'm not having Blackboard, so it's difficult for me to draw this. Let me show this using the tool. Quickly do this draw, right? So this is, for example, atom, and this is atom, right? And each atom is connected by 4 bonds. So if you want to work out what is the portion that one bond has, this is not equal division, but suppose this is equal division. So you see that this end is going to be associated with 1/4, and then this end also going to be associated with 1/4. And if this 1/4 and this 1/4 they are the same type, you have a half atoms of the same type, right? If they're different types, then you can contribute only 1/4 to one type and 1/4 to the other type. So that's basically how we get this counting. It's very straightforward. Okay, now consider all of this, then we can express again this AA, PAA, PBB, and PAB in terms of number of atoms in the system, right? So because each AA bond contributes a half A atom, so this is going to be the contribution of the total number of AA bond to the number of atom. Again, this PAA can be changing, but this 1/2 contribution will be the same, right? And again, this is the number of AB bound, and this 1/4 is going to be the contribution of the AB bound, okay, to an A atom. So altogether, add this together, this is going to be the number of A atom in the system. For the same reason, this is going to be the number of B atom for the system. Does that make sense to everyone? Why would goes to all the trouble to find out the relation between the number of atoms, the number of bonds, and number of atoms? Because before and after mixing, the number of bonds are definitely changing, but the number of atoms remain the same, right? This Na and Nb are exactly the same as this Na and Nb. Okay, does this make sense to everyone? So after that, what we could do is so this is for the demixing state, right? You find out this enthalpy for the demixing state, which is very straightforward, written as number of AA bonds times the interaction energy for each AA bond, number of BB bonds, the interaction energy for each BB bond. And here for the same expression, we have this, but then we reduce the expression by considering this Na equals to this, Nb equals to this. I'm sorry. So we write down for this case, we use the relation between Na and BAA. and PBB, etc., we reduce this expression and write down this enthalpy for the demixing state using PAA, PBB, and PAB. Okay, so again, this is by simply plugging in the expression we have for NA and NB here, and we get this. Okay, now, okay, when we have these two expressions all expressed in terms of the same quantity, we can easily compute the so-called enthalpy of mixing by taking the difference between the two, right? This is again our definition. So yes.
Before you continue, I have a question here. But this, for the ones that we've calculated using PAA and PAB, those equations only hold true for the mixing state, right? Or do they hold true even in the demixing? Will that Na equal to half PAA plus 1/4 PAB hold true?
This expression. So basically, in order to arrive here, so the first thing that we can, this is what we derive, right? This is a clear definition of H2 because you explicitly write the interaction energy in terms of the bound energy and the number of bonds, right? In here, you do the same thing. You write down the interaction energy as the number of bonds times the bound interaction energy for each bound. Now what we do here is that we express the number of bonds in this demixing state using the quantities of the number of bonds in the mixing state. And this connection is established through the fact that Na and Nb are the same for both systems.
But in the demixing state, PAB will be 0, right?
In the demixing state, the PAB will be 0, but here PAB gonna be the same PAA and the PAB you have for this mixing state. We simply express Na in terms of the quantities you find for this. So when we get this expression, the correct understanding should be this PAA is the same as this PAA. In here, we don't have any PAA. That's the reason why I use PAA to denote this mixing state. In here, the number of AA bound is lowercase NAA. So we're not doing any, so in here, in this expression, PAA should not be understood as the number of AA bound in this demixing state. It should be understood as the number of AA bound in this mixing state, yet we describe or we express the number of bonds in this state using the quantities in this mixing state because we can simplify then this enthalpy of mixing. Did that make sense?
No, but carry on. Maybe afterwards it'll become clear. Maybe.
Yeah. So again, this is
in the demixing state, are we putting the PAB factor in the H1 equation is equal to 0?
No. So in the demix, again, for this one, for the demixing state, there's no PAA, there's no PBB, there's no PAB. For the demixing state, these things are not defined. These things has no physical interpretation associated with this. Okay. It's only the number that we take from this mixing state. And we happen to be able to express, okay, the quantities in the demixing state using these numbers in the mixing state. But this PAA has nothing to do with the number of AA bounds in the demixing state. Okay. It's the number we took from this guy, okay, so that we can compare these two in a simple way. So this is, again, I know this is a little bit confusing, but you know, my suggestion is that go back and do the derivation here, and you'll see. Okay. So and then that allow us to do the comparison. Okay. So just look at the mathematical formula here. If you look at this and look at that, okay, you see that these two terms, the terms associated with AA and BB interactions, play the same role or contribute, you know, in the same fashion for both systems. And the only difference we have is the cross terms, right? So these terms associated with PAB. So and this is even clearer when you do this difference, right? If you take H2 and minus H1, okay, I collect all the expressions for you here, and if you do that, okay, you can easily find out the enthalpy of mixing, okay, equals to PAB times this epsilon. And epsilon is a new quantity we define, which equals to epsilon AB minus a half of epsilon AA plus epsilon BB. Is this clear to everyone? So we literally take this guy, this expression minus this expression. So all the terms associated with AA and BB are gone. And the only term you left is associated with PAB. And then the energy term associated with this PAB is going to be given by this. Mathematically, is this clear?
Yes.
Okay, so now let's
Yes.
talk about the physical interpretation. Why it doesn't seem to be consistent. Why in the case of H1 you still have this PAB. The thing is that again we're expressing this in terms of effective PAB terms, right? So if you look at the thing is that again you see that from this expression the only contribution of the interaction energy or contribution to the difference of interaction energy does not come from AA and BB interactions. It only comes from AB interactions, right? Because it's only associated with this PAB term. Does this observation make sense to everyone?
Yeah.
Because you have both AA interactions and both BB interactions in both systems, right? So when you do the difference, those interactions are going to be identical and they're going to cancel with one another. So the only thing that contributes to the difference is the missing AB bound, right? You don't have that in this demixing state, right? Because in this demixing state, you do not have those AB bound, right? And in this mixing state, you do have the AB bound. And what is the effective difference of the interaction energy between these bonds? You see that the contribution of this state, so we know that we don't have any mixing AB bound in this state, but we will have this mixing AB bound in this state. So we have, if we have to associate with an effective energy for those bonds, this is going to be a half of the energy of AA bound and half of the energy of the AB bound. I'm sorry, this is going to be epsilon AA and epsilon BB, right? And then you're going to compare this average to the interaction energy of the AB bound. And that interaction energy or that difference of this, interaction energy of AB bound over the average interaction energy of A and BB bound, that's going to contribute to the difference of the enthalpy of mixing. Does that make
Sir,
sense, everyone?
yes, sir. In delta H mix, so the delta H equal to PAB epsilon. So is it epsilon AB or just epsilon?
It's epsilon, and this epsilon have this expression. And you can consider that this PAB times epsilon AB going to be the contribution from AB bound, right? From this mixing state. And then this term going to be the contribution from AA and BB bound
Okay.
for the same number, PAB, right? Because in the demixing state, you don't have any real AB bound, but you can still have a number of these bounds, but these bounds are either AA or BB bound. So it takes the average, right? And it's going to give you different energy. So you get the difference of these two energy and times the number of these bounds, which you do not have in this demixing state, but you do have in this mixing state. And then this is going to give you the difference of the interaction energy. Okay. So I think that's the best physical explanation that I can offer. Again, this is a little bit non-trivial. So do not worry if you do not quite get the physical meaning for this. Right now, we're going to probably gonna have a homework. So you're going to go through the derivation yourself. And hopefully after that, you will see, it has I will not say a very, very intuitive physical meaning, but it has a hidden physical meaning there. It just needs more thoughts, I guess. So that's that. So now we see that, once we have this epsilon expression, we see a more general condition for the ideal solution, okay? So, the general condition is that if epsilon equals to 0, then we have an ideal solution, right? Now, so the previous example I tell you is that, so if we have epsilon equals 0, basically what you have is that the epsilon AB equals to a half of epsilon AA plus epsilon BB. This is a more general solution, right? This is a more general condition for the ideal solution. Now, the previous condition I tell you is that A and B atoms do not distinguish neighbors, based on their energy, which means that epsilon AA equals to epsilon BB equals to epsilon AB, right? And that condition definitely satisfies this more general condition. But here, you can have epsilon AA and epsilon BB not equals to one another, but as long as your epsilon AB equals to half of those, you still have ideal solution. Okay, but again, that's a kind of how the regular solution is more generic, and how can we use this expression we get to understand the condition for ideal solution. Okay, so now we already make a lot progress to reach here, because the goal is to find an expression, right, in terms of the enthalpy of mixing, and we're already write this in terms of the intrinsic material property, like the interaction, the energy associated with each bound, right? But this is not enough, because eventually we want to express everything in terms of the molar fraction of the atoms. So we can go back to our free energy expression and do something really cool, right? So we're still one step missing because, this is still PAB, where we're trying to express PAB in terms of, the molar fraction of A and B atoms. This now is the number of AB bound, right, in the mixing. So we're still one step further.
Professor?
Yes.
Quick question here. The epsilon AB, epsilon A, these are all for a single bond, right? For a single AB bond, the energy.
Yes, this is per bond. Yes, for single bond energy.
Okay.
Yeah. Which we could have real values for those ones. If you go to a chemistry book, you can find these numbers. But again, we have been using a very idealized, assumption. So, yeah, let me see. Yes. So, yeah, this, if epsilon goes to 0, this is going to be the ideal solution. Okay. So the solution is ideal. And the atoms for the ideal solution, this is again our assumption comes in, going to be randomly arranged, right? Now we know that in this particular case, right? So already write down this expression for you. Okay, I think this is the easiest way. So in those case, okay, in the case of ideal solution when epsilon goes to 0, it's very easy to find out what is PAB, the number of AB bound, right? And the expression is here. So this is kind of not straightforward to see, but we can work out this. So the idea is that suppose now I focused on the A atom, which is supposed to be the white one, right? If I focus on the A atom, okay, and Z here is a general coordination number, and for those two-dimensional square lattice, we can set Z equals to 4, but it doesn't really matter, okay? So if I have this white atom right here, let me highlight this for you. So we just focus on this white atom right here, okay? So we know how many number it has, right? Now, if this square lattice, how many neighbors, how many
4.
bonding neighbors? 4,
4.
right? And then in a general case, we can have Z, right? If you do not have the square lattice, but have a triangular lattice, for example, or honeycomb lattice, this number is going to be different from 4. But in general, we have Z number of neighbors. Does this generalization make sense to everyone?
Yes, sir. I just have a question. If we have two atoms A and B, so let's consider copper and silver. So in that case, they both have different coordination numbers. So in that case, what will be the formula?
For that case, we're going to deal with later. But for now, let's focus on the ideal case. For those cases, we call them intermetallic compounds, or the things that are related to real solutions. But let's stick with this and only talk about the superlattices, for which that both A and atom, B and atoms have the same crystal structure. So we'll mix them together, they still have the same crystal structure. Let's focus on that. Okay. So that's why for real solutions, we generally do not have a expression like this due to the complexity you just mentioned. But let's first focus on the case that they can form superlattices. They have a compatible crystal structure. So for that case, we know the number of neighbors is going to be Z, right? For if I'm focusing on A atom, so I know that the number of neighbors is going to be Z. But out of these Z number of neighbors, how many are going to be B atoms? How can I write down that?
In that particular thing, we have only one B atom.
In this particular case, there are only one B atom. But if we think about it, we examine many A atoms and find an average expression. Okay, so if I know that I'm sitting at an A atom, and know the coordination is Z, and in general, on average, what's going to be the number of B atoms as a neighbor for this particular, for in general, a randomly select A atom?
That will be proportional to the mole fraction of B.
There's going to be Z, because Z is the total number of neighbors, right? And
Yeah.
among this number of neighbors, how many are B?
X.
Does that make sense to everyone?
Mm-hmm.
Okay, so this is gonna be if I'm sitting right at A, right, and how many on average how many B I have, right? But how many A atoms do I have?
XA.
XA is the molar fraction. So if this is a molar system, okay, the number of A atoms is gonna be the molar fraction times the Avogadro number. This is the number of A atoms I have, right? And for each A atom, this is gonna be the a product sign. This is not going to be molar fraction. For each A atom, I have this number of B atoms as neighbors. So altogether, I claim this is going to be the total number of AB bound in my system. Does that make sense, everyone?
Yeah.
Okay, so this is exactly the same expression here, right? So I'm going to clear all drawings. So that's how we get this expression, okay? And you can easily work out this in terms of B, right? So if you, instead of sitting at A, I see, you say, I want to pick B atoms, but for the same reason, you have Z numbers, and the number of A neighbor around the average B atom is going to be Z times XA, and the number of B atoms is going to be XB times NA, so we're going to end up with exactly the same expression. So this is going to be the PAB, namely the number of AB bounds in the solution, expressed in terms of the intrinsic atomic structure, right? Like Z is a coordination number. Once you fix the crystal structure, you have this number. And X and XB are what we're looking for, are the molar fractions, right? So this is a beautiful expression. But the question for you is that, can we apply this expression? What is the condition that we derive this expression?
Epsilon 0.
Epsilon equals 0, right? So this is, assuming that A and B atoms have no preference of their neighbors. So, they're randomly distributed, they're randomly mixed, and we can have this expression. So here is another important assumption that we have, okay? This equation, holds for this epsilon equals 0 rigorously, okay? But our assumption is that we assume this equation also holds, at least as approximate, for non-zero epsilon, okay? Either greater or smaller than 0. Okay, it's for non-zero epsilon as well, as long as its value is not too large. Okay, so as long as epsilon are not too large, we still assume that this expression holds. But unfortunately, this is not true for many real solutions. And also, it's not true that for the real solutions, the two solid crystal structure always have the same crystal structure. So they have different coordination number. So that's another reason why we cannot easily apply these nice analytical expressions to real solutions. Okay. So yes, so that's another important thing that we have to realize. This is assumption here. It's okay for us to do our analysis, but again, this limits its application to real solutions. Okay, so but basically, we're going to use this expression. Okay, we're going to use this guy as the expression for PAB in terms of XA and XB for our analysis. Okay, now once we have this, right, we go back to the enthalpy of mixing. We write down this enthalpy of mixing PAB, okay, in terms of this, and this allows us to simplify the enthalpy of mixing a lot, right? So, we plug in PAB from here, in here, right? And then we regroup the terms. You'll see that we can now write down the enthalpy of mixing in terms of a material specific number. We call this omega. Do not confuse this with number of states. Now, this is just a interaction term, okay? Incorporating like the number of atoms in your system, because we're working with a molar system, so this is going to be the Avogadro number. The crystal structure, this is going to be the coordination number for the crystal structure. And then this is going to be the difference of the interaction energy between AB bound and average of AA and BB bound. But all of these numbers are material specific. For different systems, you're going to have different omega, okay? And then this part, XA and XB, are generic. So basically, we express the enthalpy of mixing as a material specific constant times XA times XB. So this is exactly the expression we're looking for, okay? So let me see what we have. Yes, so but we can clearly see that if we take a closer look at this omega, okay, we know that this guy going to play a more important role determining the physics of the system. By physics, I mean possible phase transitions in the system, right? Because as we can see, the sign of this omega, as we said before, determines the sign of delta H mix, right? Because we know both XA and XB are going to be positive. So these two guys does not contribute to the sign of delta H mix. And we already, I already treat you with our appetizer by going through, the significance of the sign of delta H mix, right? And the sign of the delta H mix is determined by this guy, okay? And the sign of this guy is determined by what?
Epsilon.
The epsilon, right?
Epsilon.
But whether this epsilon AB going to be smaller than the average AA plus BB, right? So now if epsilon is smaller than 0, This means what? This means that the interaction energy of the AB bond is lower than the average interaction energy, right? Smaller than the average interaction of a half A and a half BB. So this means that energetically mixing is favored because effectively, because AB bond has an average lower energy, right, than the average of A and BB. That makes sense to everyone?
Yeah.
And for the same reason that if epsilon is greater than 0, this means that the interaction energy of the AB bond is greater than the average AA and BB interaction, which means that mixing is energetically unfavored, but still is entropically favored. So there will be a competition. Does that make sense to everyone? So you see, that's basically where intrinsically how the enthalpy as the change of interaction energy comes from the individual interaction energy from each bond, and how this set up a competition between mixing and demixing on an energetic value level. Okay, so that's that. So now let's do that in a more consistent way. So we already have a lot of physical insights. Now let's make them more mathematically rigorous. So so this is, again, let's go back to our the long derivation. So again, the whole point is that we want to get the free energy of mixing. But for the case of regular solution, we have to worry about this enthalpy of mixing, right? And we arrived at this very nice expression, and keep in mind that omega plays a key role in determining the physics of the system. But other than that, we express this enthalpy of mixing in terms of XA and XB. And then we can take what we already derived for the ideal solution for the entropy of mixing. Again, assuming that the system does not quite distinguish different states according to their actual energy. Okay, but this is a big assumption. But anyway, we have already used it, so these are consistent, right? Because when we derive this enthalpy of mixing, we use the same assumption. So these two are consistent, and we plug these all together, and we get the free energy of mixing. This now can turn to two terms, and this last term is very familiar. This comes from the contribution of entropy, and this new term, which we just derived in this class, come from the interaction due to the interaction energy difference. So it's the contribution from the enthalpy. Okay, so now keep in mind that for regular solution, we have to worry about both the enthalpy of mixing and entropy of mixing. So now you see that there's two quantities that play important role, right? So the enthalpy of the mixing and entropy of mixing. But we know that these two are going to compete with one another. But what are the key physical quantities that determine their relative role in our system? If we examine this, X and XB are not, right? Because these are molar fractions. And except for those numbers, what are the additional quantities in the expression?
The temperature.
We have temperature. This R is a gas constant, right? This guy, is a constant, has no role. But temperature is a parameter that we can play with, right? For a given system, we can definitely change temperature. So you can actually induce different behavior. Another thing is this omega. Right? It's material specific. So if I give you iron and carbon versus aluminum and copper versus lead and tin, you're gonna get different behavior, right? So omega and temperature are the two key parameters that gonna give us a diverse range of different physics behavior. So now we're gonna spend some time to look at how if these two things are changing, how they're gonna change the physics. Okay, so yes, so let's first look at one. So we have two. Here again, let's just do this in a graphic way. So we have two key parameters, omega and temperature, right? And we say that omega can be either smaller than 0 and greater than 0, because when omega equals 0, we go back to the ideal solution, which is a trivial case. So we have two cases for omega, right? And also we have two cases for temperature. Of course, temperature is a continuous variable, but for our first analysis, we'll just set a very high temperature versus a very low temperature, right? So again, this allows us to gain some very useful, physical insights into the system without worrying about the details. So, and then we can set up those four cases. Now, the first one is that let's look at omega smaller than 0. Okay, when omega is smaller than 0, what does this mean?
It favors mixing.
This means that the system favors mixing energetically, right? And
Yeah.
we know the system definitely favors mixing also entropically. So for this case, entropy will virtually play no role, because both at high temperature and low temperature, you always favor mixing, right? So
Mhm.
now basically this is how the curves look like. Again, we're looking at the free energy of mixing, right? So this is the curve for delta H mix. Okay. So what is the mathematical form for this curve? Do you have an idea? Is this parabolic or logarithmic or whatever? What is the mathematical form?
Logarithm.
This delta H mix. We know this delta S mix is logarithmic, right? But what about this delta H mix? Okay, here.
Parabolic, right?
The parabolic, right? Because it's a very simple quadratic function, right? Because you can write down xa equals 1 minus xb, and then you see that this is a very simple quadratic term. So this is parabolic, and you can very easily show that the minimum of the delta H mix is associated at xa equals to xb at 0.5, right? This is very easy to show because you have parabolic here. So that's delta H mix, right? And this guy has nothing to do with temperature. The only thing determining this is omega. Now, because omega is smaller than 0, so we know delta H mix is going to be smaller than 0 for all composition. Does that make sense to everyone? And also your delta H mix contribution is also negative. So you have this part from the high temperature from the entropy contributions all together have a very low free energy. So both of them work together to reduce free energy in the mixing state, right? So the system definitely favors mixing. Now, how about at low temperature? How this will change the picture? Will the temperature change the plot for delta H mix?
It still favors mixing.
It still favors mixing, and it has nothing to do with delta H mix, right? But it does actually bring up the contribution from delta S mix a little bit because the temperature now is smaller in terms of magnitude, right? The low temperature is smaller. So the curve of delta S mix comes here, but altogether it's still going to add up to a very negative delta G mix. Then may not be as negative as this one, but still it favors mixing, even at low temperature. Does this make sense to everyone?
Yeah.
Yeah, it's quite straightforward. Okay, so now let's look at, so both entropy and enthalpy favors mixing. So clearly your system going to be in a, very happy state in a mixing state. Okay, so how about now we change the rule. Let's set the omega is greater than 0. So this means that
it may favor mixing depending on the value of omega.
it is may favors mixing depending on whether omega and also temperature, I would say. Let's choose omega to be a kind of a reasonable value, but we say we set a temperature very, very high. So what are we going to see here?
Yeah, then it will favor mixing.
The entropy will dominate, entropic effect.
So the thing gonna look like this, right? So basically you have delta H mix. And in this case, because my omega is greater than 0, so you know that this curve can always be greater than 0 for any non-zero composition. Does this make sense, everyone?
Yeah.
Again, this is going to be a parabolic, but it's now curved down. So the maximum is still achieved at xa equals to xb at 0.5, okay? But now if we have very high temperature, this means that you have a very large contribution of entropy, right? So the curve, the entropy always going to be negative, but if you have a very large T, right, this scaling factor is large, you get very, very deep curve for the entropy contribution. Does that make sense?
Yeah.
Right, so we will add up these two together because the entropy contribution is so negative. So the overall free energy delta G difference, delta G mix is still going to be negative for all composition. Does that make sense to everyone?
Yeah.
Okay.
But depending on the very high value of omega, if that omega curve is even, and if the temperature is not that high, but it's still high enough, this is not a set case, right?
I'm sorry, what do you mean by second case? So in this case, we set omega. So is the competition only the omega and the T, basically these, you can consider the contribution from the value of these two terms. You can set the T so high such that it can overwhelming any effect omega you have. You can always have a mixing state, right?
Yeah, but
so
that's my question. Yeah, that's my question. Like you can't always say that the delta G mix will always be negative for this omega 0 and high T.
No, you can always say that as if you fix your omega greater than 0, then really matter how large you choose your omega. By the way, there is a upper limit, right? Because for all real materials, you cannot choose omega so high. There are upper limit on omega, but there's no upper limit on T. You can choose any T you want and always have this.
Okay.
Right? So this can always be realized. There will always be a high enough temperature such that your system will always be favoring the mixing state.
Okay.
right?
Yeah.
So that's that. So it's basically, you know, how you choose T versus omega. But for any omega, for any large value omega, you can always choose an even higher T that favors mixing for all composition. That is true.
Yeah,
Okay. So the next scenario is that, you know, we you know, choose omega to be positive, but now the temperature is not as high as before. Okay. So what you're gonna see in this case?
Demixing.
And delta H mix also same like positive.
So it favors demixing.
The delta H mix is going to always be positive, right? But now my temperature is low, so this means that my entropy might not be always overcoming this you know, very high energy increase due to mixing. So this is going to give us a very interesting scenario. So, you know, the most interesting case is going to look like something like that. Okay. So this is your enthalpy of mixing. You see that this part of the curve, this contribution is exactly the same. That's nothing to do with temperature. Once you fix an omega, they're going to give you the same curve for all temperature. But now your entropy of mixing contribution is going to change because the temperature now is low, right? So you cannot pull the curve down very, very deep. You know, it's not like this. So you're going to move up a little bit. And then we'll add up these two curves together. You're going to get a free energy of mixing like this. Okay. So this means that, okay, if you have very low composition of A and B, meaning that if you just add a little bit A and B, okay, so if you just add very little bit A and B, this gives you a fairly small increase of energy. Does that make sense to everyone?
Yeah.
If you just add a very little amount of A and B, okay, it only gives you a very small cost in energy. Does that make sense?
Yeah.
Yeah, right. Because you only have very small number of AB bonds, right? The majority of bonds are still AA or BB. But this is going to give you a huge advantage of entropy of mixing, because if you just add a little bit, we showed before, the entropy of mixing is going to increase very quickly. So in the
this also means that if we have equal amounts of A and B, then it favors demixing.
not just the equal amount, right? There's a range. We'll get that later, right? So does that make sense? This idea makes sense. If you just add a little bit A or B, you know, add a little bit A and B, so you have a small cost of energy, but you have a huge gain of entropy. So that's why that, you know, for this portion, for like in here, let me draw this for you. Like in here and here, okay, you still favor mixing, right? That makes sense, everyone, right? And we'll show that, you know, there's another way of understand this. But you see, you know, when you start to favor demixing,
When there is significant amount of A and B is there.
so in terms of mathematics, what is the thermodynamic stability? What is the quantity we should be looking at that tells us the system favors?
Delta G.
Delta G, right?
Positive.
When delta G is positive, right? So basically within this range, because this is when you change the sign of delta G, right? So if your composition is within this range, I think I have a better plot for you. So if your composition is in this range, right? Okay, this curve, yeah, this window is supposed to go exactly here. So your favors the mixing state. So this means this is the interesting thing is that suppose I have a system, right? Prepare the system with different composition, right? If the first case I prepare a system with low composition. Say for example, around here, a very small amount of B and A, maybe a 3% or 2%, okay, of B and A. In this system, I will not see a phase transformation, right? As we cool the system, probably at very, very low temperature. But for the range we discussed, at the high temperature, it favors the mixing state. At the lower temperature, it still favors the mixing state. So if we have alloy, okay, with only 3% B and A, we will not see a phase transformation due to for this range of temperature we're looking at, right? But on the other hand, if I'm preparing a system at, for example, this 45% of B in A, right? We're going to see a phase transformation in this system, okay? So we do know exactly the details of this transformation, but we do know that at least, you know, in the high temperature case, right, the system favors a solid solution. They're all kind of want to mix together. But if I cool the system to this particular temperature, now a demixing state is more favored because I know mixing going to increase the free energy. So there has to be a phase transformation as I cool the system from high temperature to low temperature, right? So something going to happen to the system. So now the stable state is going to be a demixing state. Okay, so that is, what kind of the first set of insights we can get from this regular solution analysis. Okay, so let me erase this. I think I'm using up all my time, so I think this is good progress. I think, discussed all the key points that I want to touch for the regular solution. Okay, so that's pretty much, I think, the key insights that we can obtain from this type of analysis. Now, up to this point, we didn't do anything quantitatively, and there will be a lot of things that we could do by working with this model. I think you can probably see them in the homework. But for now, again, the key thing is that we introduce a more realistic model for real solution by considering the effect of enthalpy of mixing. Although the way how we consider this is still a little bit idealized, but at least we see that by considering the competition between the entropy and enthalpy terms, especially at different temperatures, we see that these two terms are competing with one another in certain cases, and it can induce a very interesting phase transformation behavior in the system. Okay, I think that's pretty much all I want to tell you for this class. I'm going to stop recording here. Stop recording.